In this problem, we have a boy standing on a beam while pulling on a rope that's elaborately connected back to the beam below him. And what we want to find here is that if the system is in static equilibrium, what is the friction force that must exist between the boy and the beam? So at his shoes, what's that friction force going to be? And what are the support reactions at A and B? So in this problem, we are given the coefficient of friction between the shoes, the boy's shoes, and the beam. So that's going to have a value of 0.4. And we want to find here the actual friction force that there must be between the shoes and the beam, and the reactions at the roller at A and the pin at B. So let's dissect this problem by drawing some free body diagrams. I'm going to start, I think, where it's going to be a little bit easier to see what's happening in our situation. I'm going to actually draw the boy first. Since the boy and the bar are not rigidly attached, they're contacting surfaces with friction, I want to separate them out here to see what's happening between those surfaces, especially because one of our finds is that friction force. All right, so I will model the boy as this rectangle here, and I need to put all of the forces that are acting on him. Now, we're not told anything about his height or his width here, so we're not going to be able to do anything with moments in this diagram, but we can still look at the forces that are going to be affecting him. So one, we are told that he has a weight of 80 pounds. So that is down, pushing him down, dragging him down. And we want to see the other forces that are acting on him. Well, he's pulling on this rope, so the rope is pulling back on him with the same amount of force because we're in static equilibrium. So we're told that he's pulling with 40 pounds of force on this rope, and we know its direction, because it's given to us, is this 5, 12, 13 triangle. And other forces acting on him. He's not falling through the beam. He is maintaining his vertical position here, so there is that contact force, that normal force between him and the beam. This is where we want to be always aware that the normal force we need to solve for is not automatically equal to his weight force, and we'll see here it is not equal to his weight force, except in some situations it can be, but in general it's not. So N, that normal force between his feet and the beam, we are going to need to find. And finally, we are going to have the force, the friction force between his shoes and the beam. So again, that contacting surface is horizontal. That's what makes the normal force vertical. It's orthogonal to the surface of contact. The friction force will be horizontal. So we need to determine its direction, though. Is it pointing left or pointing right? In this case, we would presume if the boy is pulling on that rope, if he were on ice or something very, very low friction or zero friction, if you pull on that rope hard enough, you are going to move to the left. So we can think about this as the boy wants to move to the left relative to the beam in the absence of friction. Therefore, since there is friction, it's going to be in the opposite direction that he would want to move in, or that motion would be directed towards. So we can say that that friction force is pointing to the right. And again, the math will check us on this. We want to make sure the N and the FR are both positive. Otherwise, we might need to redraw and resolve the problem. But we can try to use some insight here to guess, or have an insightful guess of which direction this should be pointing. So if you were on something very smooth, he would be traveling to the left when he pulls on the rope. So therefore, that friction force that's preventing that motion from actually happening must be in the opposite direction, the right. So that's our complete free body diagram. Notice here for that normal force, since I don't know anything about his width, I'm not putting in that unknown distance from a pivot point. I'm unable to check for tipping. I'm only looking for him slipping in this problem. So looking at picture 1, actually, I will only be able to get 2 equations out of it since I don't know any of the dimensions to do a moment equation. I will be able to solve for the normal force and the friction force, 2 equations for those 2 unknowns. So I'll come back to that. I actually will go now and draw my second free body diagram while I'm here. I will draw what's happening on to the beam. And really the picture I'm going to include here, to be technical, in my picture I will include the pulley itself. And just to kind of illustrate this a little bit better, I'm going to keep some of the rope and some of the rope at C as well. And so my object is actually the entire blue beam, not the supports. I'm going to be modeling those separately in a moment. I'm keeping the pulley at the left end. I'm keeping a little bit of the rope, but I'm going to cut through it, and we'll see why that's helpful. And a little bit of the rope that goes from C down to the pulley, but I'll be cutting through that as well. So this is just that object that I'm isolating from the rest of the system. So let's see what's happening to it. And here I'm not including the buoy. I will include, though, what the buoy does to the beam. So let's go through this. It's a little bit complicated. So 2, we're going to have 5 feet to go from the left end to D, where the buoy is, 1 foot between D and C, 3 feet between C and A, and 4 feet between A and B. So I'll put just those dimensions down first while I am here. Now I need the forces, and if there's any couples, they're acting on the system that I kept. Let's start with the ropes that I cut through. So again, I kept some of them. I kept the pulley, so I can't see what's happening at the axle of the pulley. I don't want to, I don't need to. But where I cut through the rope, I'm able to see the tension that was in that rope. And because it's one continuous rope from C down to the pulley, around the pulley on the left side up to where the buoy is pulling, it's the same tension the entire time. And since I know he's pulling with 40 pounds of force, I know it's 40 pounds at each of those locations, since it's one continuous rope, neglecting the belt friction at the pulleys, and it's static, so it's 40 pounds at every point in the rope. And what do I know here? I know it's still that 5, 12, 13 triangle up here. And at C, this is going to make a 60-degree angle with the vertical. And I know that by using alternate interior angles, that if that's 60 over there, that's 60 over there. Okay, so that takes care of the tension in the rope. There's still a lot of other things to contend with here. Let's look at A, that roller. Well, I'm going to have just a force in the vertical direction. It allows travel in the X. It allows rotation at A, so only that vertical reaction. And B is a pin, so I'll model that as a horizontal component and a vertical component for that BY. Now, the buoy we're treating him as basically a particle centered at D, so we have to have that equal and opposite force. We have that N pointing down in this picture, and we have the friction force pointing to the left at that point D. It has to be equal and opposite as it was in picture 1. The friction force was to the right, preventing him from moving to the left. Therefore, it must be pointing to the left in picture 2, and that's representing his feet kind of dragging along that would be pulling the beam to the left. And finally, we don't want to forget about this. I really should put in the given. Really the weight of the buoy, I'll put here so we don't forget what the difference is, was 80 pounds. But we actually do have the weight of the beam to contend with of 100 pounds. It's uniform and has a weight of 100 pounds. Since it's a uniform beam, that means that its center of mass is just going to be at the center of its length. So there's the weight of the beam itself of 100 pounds, and that is going to be at half of the length of the beam. The beam is going to be 13 feet total in length, so that's 6.5 feet from either side. So we do have in picture 2 a decent amount going on here between the tension showing up at 3 places, the effect the buoy has on the beam, and those reactions. And in this is a case where we actually are contending with the weight of the beam itself. If we look at these 2 free body diagrams, we have 2 equations in the first picture and 2 unknowns. We only have 2 equations because we can't do a moment equation in picture 1. We don't have those dimensions. In picture 2, we have added an additional 3 unknowns, A, Bx, By, However, in picture 2, we can, it is a rigid body, a 2D rigid body, that will give us 3 equations because we do know all of those dimensions. So we can go on and write our equations out. So starting with our first picture, this will be fairly straightforward to get some results. Let's sum forces in the x direction. I will have, according to my coordinate system, FR all is pointing to the right, minus 12/13 of 40 pounds. And equation 2, I'll do the y direction. I will have my 80 pounds down in the negative y, plus the normal force, minus 5/13 times the force that he's pulling on the rope with, 40. So looking at equations 1 and 2, 2 unknowns, 2 equations. I'm actually going to solve them now to make the steps a little bit easier later. So solving equation 1, I can find the force of friction between his shoes and the beam is 36.9 pounds. And equation 2 then, the normal force between him, the boy, and the beam, or his shoes and the beam, is 95.4 pounds. Notice that's not his weight, is different because he's also pulling on that beam. This force of friction was one of the values I was asked to find in the find step, so 36.9. I will be verifying that after the fact in a moment, but I just want to solve my equilibrium equations first. So we know the force of friction in order for static equilibrium to be maintained is that 36.9 or 37 about pounds. And we found his normal force. Again, it's larger than 80 pounds. We want to just be aware of that. Right, that's everything we can do from picture 1, are those 2 equations. But now we can go on and we can look at picture 2. So to start, actually, I'm going to take a moment about B in this picture, because now I will have only one thing I don't know left at this point, and that is A. I already know N from equation 2, so A will be the only remaining unknown. So taking the moment about B will eliminate BX, BY. So let's see what is the moment around point B. I already know it's going to equate to 0. So I'll move right to left. So the first thing I'm going to encounter is A, and that's going to be clockwise, a minus 4A, plus 6.5 times 100, and that is counterclockwise, so positive. Then we have the vertical portion of that 40 pounds located at point C, so that's also going to be positive, so 40 times the cosine of 60 is actually going to be the vertical component, and it is going to have a distance of 7 from point B. This 3 is measuring from A to C, plus then 8 times N, which I already know the value from equation 2, and then I'm going to have at the end here, plus I'll do the 40 pounds down first, so 40 pounds times 13 minus, and then actually the vertical portion of the 40-pound tension that's up and to the right, that's actually also 13 away, and its vertical component is going to be 5/13 times 40. So it does a lot of terms here, but the only thing I don't know at this point is A, so this is going to be easy to solve. So while I'm here, I will also write the other equations. Summing forces in the y direction in picture 2 is going to give me a negative 40. I'll work left to right, plus 40 times 5/13 from the tension that's up and to the right, also at that extreme left point. And I will have a minus N minus a 40 cosine 60. I will have minus 100 from the weight of the beam itself, plus A plus BY. By the time I get to equation 4, I will know A from equation 3. So finally, I will have 5 Summing forces in the x direction in picture 2 will give me, again, I'll work left to right, a positive 12/13 times 40 minus the force of friction, which I already know, minus 40 sine 60, and a plus bx. And here bx will be the only thing I don't know. So going to the solve step in 3, solving that, A is able to be solved for is 468 pounds. I assumed up, it's positive, so my assumption was correct. Equation 4 now, I know A, I know N. By, I don't know. By, I get a negative 228 pounds. It's negative, so I assumed it was up. It's actually down, and that's okay. It's a pin. It can be pointing down. And equation 5, Bx, I can solve for 34.6 pounds. And that is positive. I assumed it was to the right, and it is indeed to the right. So the other things I wanted to know were these reactions, A, By, and Bx, and I've solved those as well. So let's just go back up to the find and mark that. We have the reactions at A and B. Now, one thing we do want to check here is we do need to verify that the buoy would not be slipping. This whole all the equilibrium equations are under the premise of equilibrium. So we have to make sure that this scenario is possible, that it's feasible. I assumed when I wrote these equations that he was not slipping. That means that the force of friction that we're asking for, the 36.9, has to be viable. So we do have to, in this case, check, is it possible for the friction force to be that high? Now, notice I didn't max out the friction force. Nowhere did I say the friction force was mu times n. But now I do have to do a check here to make sure that it is actually less than, or it could be equal to. So I'll have a verify step here. So the force of friction must be less than or equal to mu times n. So that's the question we are asking. So if it's true, then equilibrium is maintained. If it's false, actually all the equations were done under a false premise. He would actually be sliding on the beam if he were pulling with 40 pounds of tension. So let's check, make sure this is true. So 36.9, is it less than mu times n? So we actually didn't even use the mu yet. Mu is given to us is 0.4. So is it less than 0.4 times the normal force? The normal force we found 95.4 pounds. So simplifying this, 36.9, is it less than or equal to 0.4 times 95.4? That is 38.2, and yes. So let me double put a check mark here. Yes. All right. The most the friction force could be without him actually sliding was 38.2 pounds. For this equilibrium scenario to hold true, we require 36.9 pounds, which is less than the maximum it could be. It's pretty close, but it is still less. So this verifies that under these conditions, he indeed would not be sliding. If he was pulling with 40 pounds of tension, this would be completely in static equilibrium. So this validates what we were going through with these equations 1 to 5. It is indeed in static equilibrium.